The world is going to Python, right? But I don't think computer science is going to Python. Maybe I'm wrong. Maybe I'm just a holdout to this. Like, I don't think systems development is going to Python. I could be wrong, right? I mean, Circuit Python exists, and what's more systemy than writing than embedded code? So I don't know. I don't know. It pains me. What am I doing? I'm telling you the next thing, and I got to get through it. When's class end? 12:35, because it's going to be your next one parts of your next lab. So let's. I just did Alice. No, I got another Alice. Okay. All right. A new topcoder problem. Again, another G1250, another one involving Alice. So Alice is playing a game with her friend Harvey. Why? I just like my dog. God rest his soul. They're playing a game with coin flips. Actually, I guess Alice has to flip the coins for Harvey, right? Because he can't really flip those coins. All right, they're playing a coin flip game, and the game's going to be composed of multiple rounds of coin flips. Whenever it goes heads, Alice wins. Whenever it goes tails, Harvey wins. And the point allocation starts at 1, then 3, then 5, then 7, just adds 2 every time. So we got a 5-round game here, 5 coin flips. Alice gets rounds 2 and 3, so she gets 8 points. Harvey gets 1, 4, and 5, so he gets 17 points. Harvey wins. That's the game. The coin flips reminds me of sports gambling. Do y'all want a 1-minute digression on what's on my mind with sports gambling? We got a yeah. All right. When DraftKings gives you a promotion on parlays, okay, if they give you a 25% promotion on parlays, and a parlay is going to be a multiple stage bet. It's like coin flips. That's why I have this. A parlay is going to be, like I say, Tennessee is going to win by over 4, and in the next game, LSU is going to win by 5, and in the next game, Georgia is going to win by 6. And I have to get all 3 of those to win. And they give you 6-to-1 odds on that bet. If they're all 50-50 bets, they give you 6-to-1 odds on it. It's a 7-to-1 bet, right? It's coin flips, right? Because there are 8 ways to flip 3 coins. Why was I going on with this? I'm at the point now. So when they give me one on a parlay, I bet it. I bet $5 on it, and I flip coins. I roll dice to choose because I believe in probability. And I'm getting killed right now. And that's what's driving me nuts. And I know, because, this guy, in a 1 in 8 bet, right, what's your expected return on this is like $1 a bet. You're expected to win 1 out of 8. But randomly, I mean, you're going to go through dry spells, right, of 20 and 30 bets. And that's hard emotionally. So, but I'm doing it. In the drive-in, I was like, should I stop? I'm like, no. Not going to stop. I've allocated $150 to this, so I can go through a dry spell of 30 bets without going out of money. Stay tuned. All right. God, I got all sorts of random shit to say. Have you ever heard of the martingale? Anyone? I got a nod. Martingale's a betting strategy on a coin flip. It's a coin flip, good, so it's relevant to this problem. The way the martingale works is you bet $1 on a coin flip. If you win, cool, pocket. Bet $1 on the next coin flip. If you lose, you bet $2 on the next one. And then if you lose the next one, you bet $4 on the next one. With the idea of you're going to win eventually, and when you win $1. Right? So it's crazy, and that's like a gambling strategy from forever, from like the 1700s. People would gamble using that strategy. What's the problem with the martingale? You're gonna have a dry spell that kills. You're going up powers of 2 here, right? So you're gonna have a dry spell that bleeds you dry, and then you're gonna lose all your money. That's the problem with the martingale. If you had infinite money, the martingale would be great, but powers of 2. I mean, powers of 2 go up fast. Okay, top coder problem. All these things you've learned that you can't tell anyone, right? Your friends don't care, do they? They don't. My wife doesn't care. I'll tell them. She'll be like, I'm calling my sister. Okay. Actually, I'll give Emily props. Emily cares, but she's a computer scientist. Okay. Oh, okay, so now here's the problem. you're given two numbers, Alice's total score, end score, and Harvey's total score, and your job is to return the minimum number of rounds Alice could have won to achieve that score. So in this one, the answer is, if you're given 8 and 17, that happens to be the answer here, or the problem specification here, the answer is 2, because the minimum number of rounds Alice could win is 2. And she could have won the 1 and 7 round, but if you enumerate all possible, coin flips, you will come up with the answer being 2. Okay, and then if it's impossible, you return -1. Okay? This problem is a little harder. Like the last problem is like graph problem, no problem. This one is one of those top coder problems where I can tell you when I first saw it, I'm like, I don't know how to solve this. I mean, honestly, I don't. So what do you have to do? Well, you do look at the constraints, because if the constraints were like the number of rounds is going to be, 10 or 20, then I'm done, right? I'll enumerate. If it's 20, I can enumerate, because that's 2 to the 20. I can do that in top coder, right? But it's not 20, right? So A and B are between 0 and 10 to the 12th. Freaking long. Thanks, top coder. I hate longs, right? And 10 to the 12th is 2 to the 40. Top coder, you get about 2 to the 22, 2 to the 23 before you run out of your time limit, depending on how tight your code is, okay? So what do? Well, what I did is I started probing around and looking at solutions and looking at some answers, just doing examples. And what I realized fairly quickly is that A plus B had to be a perfect square. I just did that by looking at values, right? I didn't prove it. You can prove it. It's actually a very easy proof. I'm not going to go through it, but you can prove it has to be a perfect square. So that's nice, right? Our first test is A plus B a perfect square? Second observation, now this is just by looking at the constraints, okay? A and B are limited by 10 to the 12th. So the number of rounds, okay, as it turns out, the number of rounds squared equals A plus B. So the number of rounds is going to be limited by 10 to the 6th. I can do 10 to the 6th in top coder, that's 2 to the 20th. So if I can find myself a solution that is linear in the number of rounds, okay, I've got it. Now, some of you are probably thinking, I should ask you to admit that you're thinking this, that you could solve this mathematically. You don't need to actually write an algorithm, right? All the time with top coder, if I can solve it with an algorithm that I know how to do, rather than a mathematical equation that I might get wrong, I always do the algorithm. Right, because I know, right, that last one, I know I can write a depth first search. Here, if I get to write an enumeration in 10 to the 6th, I know I can do that. Proving my mathematical equation works, I can't do that. All right, I don't trust it in top coder. In life, yeah, you might need to do that. Okay, another observation is that if Alice's sum is 2, it's always going to be impossible, right? Because the first round's 1, the next round's 3. You can't get 2. Okay? So, corollary, if I've got A plus B minus 2, then one of them is 2, and that's going to be impossible. But every other sum is possible. Right? I've just enumerated them here for if the number of rounds is, if A plus B is 16, so the number of rounds is 4, right? I can enumerate and figure out that they're all possible. So I believe, I haven't proved this, but I believe that you can always find a solution if A is not 2 and B is not 2. Okay? So that's good. So now let's figure out our approach. This is my approach. So again, this is just as me plugging in, trying to figure out how am I going to solve this problem. What I came up with was, and we'll look at the base case. If Alice's score, and let me just make Alice's score the minimum of Alice's and Harvey's scores, right? That'll make I'll swap them if they're off. Okay. If Alice's score is less than 2R, I can solve this in O of 1. Okay, we'll go through it. So if it's greater than 2R, now I need to have an approach. How am I going to solve this? Well, my thought process was, if I can reduce the number of rounds by 1 each time I'm linear, okay? So if I can make a recursive call where I'm reducing the number of rounds by 1, which is going to reduce A by this maximum amount, that's just math, okay? I don't expect you to understand it intuitively because I don't, right? But my intuition here is I'm reducing the number of rounds by 1. If I can make a recursive call that always reduces the number of rounds by 1, Now I'm linear, I've solved the problem. Okay? So that's my goal. When I was solving the problem, this became my goal, is can I do a recursion where it's the demarcation point is 2R? Okay? So if it's 2R, less than 2R, then A, if it's odd, the answer is 1. Okay, now here's the example. Here's my proof by Cosmo, right? If I have 3 rounds, okay, then my number of possibilities is 8. If I look at all the odd ones all fall out of just winning 1 round. Okay? That gives you the odd number. So that's 1. If it's even, then if it's 2, then I can't do it. But if it's not 2, then it's just add 1 to a round. Right? So then my answer's 2. So now I've got my base case solved in O of 1 time. Okay. How about the bigger one? This one's a little bit harder. So what I came about, and again, I didn't prove this. This was just intuition. Was what I thought, if it's that big, I'm going to give the highest possible score to Alice, the highest round to Alice, and now I'm going to solve it recursively. Okay? I'm going to give the last round to Alice. Okay? Because I'm trying to minimize her score. That makes sense. So the question is, does it work? So I've got examples here. Here's my recursion. I start with r equals 4. Now I go to r equals 3. Now I go to r equals 2. Right? The ones that don't have arrows are the base cases. Right? So all the ones with arrows, these are the recursive calls. And you'll note with all the recursive calls, they have a nice little pattern. Right? Remove the 7. Remove the 7. Impossible. Remove the 7. Remove the 7. Remove the 7. Right? They all work in the way I want, with the exception of this one. This one doesn't work because when I remove the 7 here, I get 2. And I know 2 is impossible, but I know it's possible. So when you look at these, when they happen, I guess it only happens here. What is it? It ends up, if we extrapolated this out, it's always the very top arrow does this. Okay, well that's a special case, right? The very top arrow is going to be 2r plus 1. So I can just put that into my base case, right? Instead of stopping my base case at 2r, I'm going to stop it at 2r plus 1. And I'm going to have special purpose code for this, where my recursive thing would say it's 2 and impossible. So that one. Oh, look at me putting math in there. So when that happens, the answer's 3. So now I've got an algorithm. And I know I said on Tuesday, don't put algorithms on your slides, right? Because they're too busy and no one cares. Well, here it's actually small enough, I think it's nice to put it there, right? So you're going to check to see if it's a perfect square. If not, you're done. Then you're going to set r to the square root of the rounds. And then you have base case and recursion. And your base case goes up to 2 to the r plus 1. And then your recursion is going to reduce the number of rounds. And that's it. And now that gives you linear, and you're done. Okay, good, class isn't done yet. All right, so here's the running time. Right? It should be O of R. O of R means it's O of square root of N, of A. And N is A. So this is Alex's score. Alice's score, I gave Harvey a score of 1 because it's actually the hardest case to solve. And you'll note, that looks like square root of N, doesn't it? That's a square root looking slide. Again, proof by Cosmo, I didn't prove it, but that's what I would expect. Okay? I definitely pushed out past the constraints. Constraints are 2 to the 12. So I pushed out to 10 to the 16. And if you actually write it with recursion, it fails. And it fails right here at that value. Oh man, so it fails past the top coder constraint, doesn't it? The top coder constraint is 2 to the, that's not 2 to the 12, that's 2 to the 9. Why? Ran out of memory, right? Because recursion uses stack space. So I ran out of stack space and seg faulted. So I have to so this is one where I have to take out the recursion. It's recursive, but that's easy to take out the recursion on this one, right? Because I'm just doing r minus 1. So I can do it iteratively, as in dynamic programming. Okay. You might be able to solve this algebraically. I never have. I don't know if students do. It is a lab, so if you do it, yay for you, okay? But I wouldn't rely on it. And when our values get really large, can we trust square root? Right, because square root's a floating point. So when I actually wrote this code, when I wrote my code for this, I actually didn't rely on square root. I calculated it myself. Did I? Using binary search? That sounds terrible, doesn't it? Actually, I think what I did is I called square root and then I double checked and made sure that the answer was correct and then adjusted it if it was incorrect. All right, you can do this even faster. I've beaten this problem to death, haven't I? Okay. But you can do it faster, and the way you can do it faster is you can say, look, if I give the big rounds to Alice, she's going to win some number of big rounds. And then there's going to be a point at which it's impossible for her to win this number of big rounds. If I give her all these, it's going to exceed her score. So, but if I can find this point, then it's actually an O of 1 calculation to figure out the rest. So, I can do a binary search on this value, H. Right? I can say, I know if I give Alice 0 rounds, maybe it's doable. I know if I give Alice all the rounds, it's not doable. That gives me my binary search decision. And then I can do a binary search on what's the largest value of H where it's possible for Alice to have her score. And then once that's done, it's O of 1 because this actually fits in the base case. So you could calculate this mathematically, but it's easier for me to use binary search. That's one of those things. Do you all trust your binary search abilities? Like, would you bet your kids on your ability to write a binary search? I wouldn't. I'm just telling you right now, I wouldn't. Binary search is hard for me. That's why I did a complete unit on it in 302 for the first time last semester, was because I realized when I was doing leak code problems that every binary search problem gave me a hard time. I figured it's giving me a hard time, it's going to give you a hard time. But that's the solution. So you're doing this as a lab. I'm bumping the constraints past 10 to the, my constraints are big. They're probably 2 to the 64, right? Because I want you to think. And so now you, when you're solving this, can either try to do math and get it right, or you can't do the recursion that I gave you because now R is 2 to the 32, and you can't do that fast enough. So you're going to have to do this binary search and O of 1, or you have to do it mathematically. And I'm going to tell you, this and the problem in your first lab, they're harder than you think they are. They're harder than I think they are. They give students more problems than the students think they should get with them. I'm just telling you that right now. Often you size up a lab and you're like, oh, this one's going to be hard. This one you're going to size up and be like, okay, I'll wait till the last night. Don't, because it gives students a harder time than they think. Okay, that's just me giving you a nice thing. All right. Now, the talk. Sorry, let me go. In the talk. Oh yeah, sorry, I always forget this. This one was hard, right? The top coders were 25% on this problem. On a D1 250, so it's the problem they all started on. Why? I'm betting they use math, right? A bunch of them use math, they got it wrong, and then I'm guessing a bunch of them did recursion and didn't spot the case where the recursion fails, right? So you didn't need to do the binary search to get it right, but that's what this one, this is a hard problem. Top coder, people who do top coder are good, by and large, and so 25% means that's a hard problem. Especially 28% of the solutions were correct. Often they don't submit them when they can't get them because they know they don't get it right. It's rare that you submit a problem. If you have a bug, yeah, but it's rare that you submit a problem and you're going to get it wrong. What I do, I've told you this, I'm sure my salute with Top Coder. Back when I cared about Top Coder and I actually would do it live competitively, I'd solve it and then I'd submit it. And then I'd spend 10 more minutes to see if my submission was correct. And then if it wasn't, I'd resubmit it and eat the penalty, right? Because that was my strategy because 80% of the time I'd get it right if I submitted it. But I also knew I'd make mistakes. All right, so about the talk. This slide I don't think is a good slide. And this is a slide I gave you. But you will notice I didn't read the bullets. Right, your thought is to read the bullets, and it's funny. My notes, when I go through this lecture before I teach it, my notes actually instruct me: make sure you don't read the slide, make sure you tell the story, and don't read the slide. And so I tried to do that when I gave the talk, rather than reading the slide, because otherwise, there are around. It's not going to come out well. But in general, I don't like this slide. I think it has too much work and it requires too much thought. Okay. Oh. Well, I forgot about that. Yeah, since this is a lab, I do want my slides to be reference material for you. So that's part of the reason why the slides have a bunch of information on them, is because that's good reference material. I want this to be reference material for you. Okay, this one. Were you thinking it? He told me not to put math on a slide, right? And again, part of it is because it's my reference material, but you'll notice I didn't go through this math, right? Okay. This one, right? Although I put it there, I did not attempt to explain why this is a minus 2r minus 1. When you think about it, and you will, because you've got to program this up, you'll realize that this is correct. But conveying that intuitively in a talk, impossible, right? But I can get that intuitively. So that's what I hammered on in trying to explain this. Okay. All right. So I already went over this, right? Is that it? I told you not 2 algorithms, but this one I felt it was important to have the algorithm in one slide, and it was small enough, and I used the colors, right? I used the colors to go base case recursion to try to give you a roadmap. Okay, this was my slide in 2015 of the one that had the pictures of Alice and Harvey on the bottom. And this slide is actually more mathematically correct than the one I gave you. I was trying to give you intuition on this one, and I acknowledge that I'm guessing 80% of you don't really understand what I'm saying here. It's hard. So it's hard. And I can say, if I were in the audience, I don't think I'd understand what I was saying here. But what I'm hoping is when you go over these slides again and you go over the example, you'll go over examples, hopefully, you'll realize what I'm saying. Okay. So, and in some respects, when you're giving a talk, this isn't a bad thing to do. To do something, try to give some intuition. You know your audience doesn't really understand it, but you know when they go back to the talk or go back to your paper, if they care, they will. Yeah, this is better than the one I gave before. Okay. All of that is done, and that is done. This is going to be a lab, so I'm going to open the lab when I get back to my office after 360 today. I'll open up the lab. The lab is 2 parts. It's this one and the one I'm going to go over on Tuesday. Okay, but you can start on this one now if you want. You can start on one Tuesday if you care. You can look at the material online. And then we're all good. Do we have any questions? Okay. Well, it's 10 minutes early, and I know I say every minute is precious, but I got nothing prepared after this, so I'm not going to start on the next problem because I don't think it'd be good. Actually, history has shown me it's not good to start on the next problem and not finish it. So, unless we got a question. Okay, Calvin.
Read scripts for this lab?
I don't know. That's a good question. I have no idea. I don't think I do, actually. I think you got to rely on Jacob for this one. So, the Alice one, so all right. Sorry, I know you're like busting the guy here. Alice is easy. You can come up with your own test cases for Alice. You can write your own grades. I don't know if I did or I didn't. It was simple. I've got a working program in the lab. Both of them have a working program in the lab directory. So you can test yourself. Alice is an easy test. The next one, I know I have either files or a tar file of 50 examples. And I think that's what Jacob will use. So you have it there. Adam Disney made that back when he was a student here. So he did that. Okay. Any other questions? Do you have a question? Oh, you do not. Okay. See ya. Have good weekends.